I have the honor to start, or to sort of start the transition to the more lab demo part of this two-day event here. That's why we take the opportunity to tell you a little bit about where we are here, SYSLAB. That's you are actually sitting in part of the laboratory, but the laboratory itself is quite large. It extends about like half a kilometer in that direction and half a kilometer in that direction. And I will tell you a little bit about why we built this, or why we thought there was a need to build this, and how we built it, and what is in it, and what you can do with it. And then right after that, one of my colleagues will take over with with one of the laboratory demos that actually uses SYSLAB. I should also quickly mention that SYSLAB is part of PowerLab DK, which is an umbrella of different laboratories that DTU has access to. And so SYSLAB is basically the instance of PowerLab that we have here in Risø. I will start with kind of the way that we think about this whole thing, or why did we build this? And it is because when we started thinking about smart grids some time ago, we kind of realized pretty quickly that kind of the key issue, or one of the key issues, is the integration of a lot of very small resources that are in the grid. So you've probably seen that picture on the left side quite often, which is sort of what we kind of have the units that participate actively in control of the grid today. This is kind of, you see all this little yellow dust over there. That's sort of our vision of what we want to do in the future. We want to have a lot of units out there, household-sized, electric vehicle-sized units in companies that we control. You've heard a lot of that already in presentations before me. Which means that we're going up to a much larger number of units, and we're going to a much smaller, more compact size of units, and that has a couple of consequences. There is a very large number of resources, so that gives a problem with, does it scale up from thousands of units to millions of units? These units are typically connected with very, very low specification communications. I mean, a lot of, if you're talking to somebody's household, it's going to be over a private broadband connection typically, or something that has a reliability that is similar to that. There is a problem with a continuous rollout, because that's a system that's not going to be deployed overnight. That is coming bits by bits and pieces here. So this is something that will happen over a long time, and the system will have to function at all times. So there's no timeout that we can just take everything down and then we change everything and we put it up again a week later. That's not going to happen. So there's a continuous rollout of smart grids that has the consequence of a very heterogeneous system and also a very dynamic system. There is a direct interaction with end users, much more direct than any of the assets that you have in a power grid today. That has obviously security implications if you have suddenly things that happen in people's homes and have access to the networks that control things. That's also obviously a flexibility issue. And then as part of smart grid research, there's a lot of control concepts that have surfaced that are sort of different from the way that grids are being controlled today. And we wanted to have a facility to test some of these things, or to at least get an idea of how these things behave before you would go to test it in the field. I think we can skip that mostly. There's a couple of kind of concepts that you know that have been developed for control in distribution grids in particular. You've heard of cells. You've heard of active distribution networks. Virtual power plants is a concept that has been explored quite a bit. Microgrids is also something. So we kind of wanted a facility where we could try these different concepts. In order to have a test bed that can sort of do these things, we realized pretty quickly that you cannot enforce a particular architecture, or the lab cannot enforce a particular control architecture. I mean, if you take a traditional sort of automation approach, you sort of have, does this thing have a laser? Yeah. You typically have a central master that knows everything, controls everything, and you have a lot of slave systems. The problem is, how do you, if you want to test a distributed control approach, like, for example, an aggregated system where you have a master that controls some slaves that are themselves masters that control more slaves, or if you have something even more radical that has been, floated many times in context of smart grids, where you have actually a peer-to-peer system that doesn't have, at least not a fixed master. How do you test a thing like that in a system where you are sort of limited by a setup like that? So we figured we cannot have that. We need to go a little, we need to sort of set the system up in a bit more untraditional way. And so the key concept behind SYSLAB is we have a lot of assets around, a lot of distributed energy resources, and each of them has one of these boxes here. If these screens were not there, you could see a few, but most of them are actually out in different locations out in the field. Each of them run a more or less identical copy of our software platform that we've been developing. SYSLAB is about 9 years old now, so that's the time we've basically spent on it. And they can communicate with each other, and we can use that to deploy different types of control on there and let, for example, define, okay, this one box is an aggregator in this concept, and it will talk to some other units. But there's nothing in the lab that will define that up front. It is something that we define when we set up an experiment. It gives us a lot of flexibility. What do we have in terms of energy resources? There's 3 photovoltaic systems around in different in different places. We have 2 wind turbines connected to SYSLAB. There is a diesel generator set sort of as a traditional fossil generator, can also be used as a grid forming unit. We have 3 buildings in SYSLAB. So there's one old office building. I will tell a little bit more about these buildings later. And there's 2 residential buildings that we just got about a year ago that have also been connected. We have various types of load simulators, so we can go and in different parts of the grid simulate that we have a certain load behavior or something like that. We have some storage. There is a vanadium redox flow battery. There are some electric vehicle batteries, minus the vehicle. Then there are some electric vehicles. We have a little fleet by now that is including the vehicle that we can control. And then some other units. We have a capacitor bank. There's a back-to-back converter that allows us to move power in and out of the grid in a controlled way. And we just so people start giving us units that they think we might want to test. So we get this hydrogen-based combined heat and power plant that we don't have the money yet to connect, but it's kind of nice that people say, "Oh, you have this big system. It's, wouldn't you be interested in having this type of unit or so?" The second, I think, distinguishing feature of SYSLAB is we have a very complex and flexible grid in here. That is the layout that we have. There are 4 substations right now. You are basically sitting in one of them. You kind of just see some of the switchboards behind the walls now. And we have what is called, as a central unit, a crossbar switch that allows us to connect these substations together in different ways to create many different types of grid topologies. And that's actually one of the really, really useful features. We made back then, when we started adding the 3rd substation, we just made a little study of sort of different ways that we can connect things just based on 3 sites, where you can have 3 sites all connected together as one system, or you can have them as 2 parallel systems, or you can have 2 sites connected with strong cables, and then the 3rd one with a not so strong cable, because you only use 1 and not 2 cables. And so there's kind of a lot of combinations. And what we can do here is we can do very long feeders. We can, with the latest extension that we have, we can go up to 3 kilometers. From end to end, from a grid connection to, for example, a house or a PV unit at the end. We can make trees, so that's when the crossbar as it is right now. We could, for example, simulate a substation that has sort of 1 uplink and then 7 feeders down. We can run multiple systems in parallel, which is in practice very useful because people sometimes want to do multiple experiments in parallel. So since it's a shared facility that quite a lot of people are using. And we can use the grid or part of the grid as an isolated system or as a grid connected system. And it's not limited to sort of traditional distribution grids, but we can also mesh the system to make experiments with that. I would like to go a little bit into detail on 1 type of component that we have here, which is our houses. One of the reasons I'm going into detail is that they're going to be used in 2 experiments, one that you will see today, one you will see tomorrow. That was our first flex house, as we call them, which was just an office barrack that was left over, that had been evacuated, and it was very nice because it was electrically heated. So we figured that would be a very, very nice addition as a controllable load. And so we put a lot of sensors in that building, occupancy, temperature, metrology. We can see if the windows get opened or the doors get opened. And we can control all the space heaters. We have air conditioners in the room, so we can control, and we have a hot water system that we can control, and some appliances. And this is electrically connected to SYSLAB, and it's also integrated with SYSLAB on the IT side. So it's, yeah, we can basically use it as a smart house for our smart grid. Recently we got 2 real houses because that office barrack has some disadvantages, of course. It's first, it's not a very realistic house. It's the walls are very thin and nobody lives in there. It's another problem. So we got 2 houses that are actually on the other side of the street. And those are really real single-family homes. There are some former guest houses that research was using for the researchers. And we've also equipped that with a lot of sensors. And these have, which is much more typical for Denmark, waterborne heating systems. So it's a classical water-based central heating systems. And we have taken these 2 houses and connected them to a heat substation, because we are starting to get interested in the interaction between electrical and other energy systems as well. In this case, what we would like to do research on with this facility is district heating systems as well. So we started to build up a little, we call it a heat substation, where we can take different heat sources and heat storage and heat consumers, and also connect them together in different ways, very control the flow, measure where the energy is going, and so on. To, for example, see how you could store excess electrical energy in district heating water to be used later when you need the heat and so on. Right now we have basically a connection to the original district heating that was there, and we just got a big heat pump installed there that is able to supply both houses. And we have planned, if we get some funding for that, to add a natural gas combined heat and power plant there, a solar thermal system, and hopefully also a storage system that will give us some flexibility. This is also connected electrically to SYSLAB, and it's also integrated in our IT platform. So we can play with these houses as we can play with all the other resources. Don't read the small text. This is also something it's a slide that was taken out of our planning process, and it's again similar to the one with the 3 electrical sites. We started making scenarios of what you could do with such a heat bus bar. So we have kind of different sources of heat pumps and district heating and solar and so on, and then we have the 2 houses. And we starting to make that list, we figured, oh yeah, there's actually quite a lot of combinations. And then we wanted to go and ask some plumbers to make such a heat bus bar for us, and it took us about a year to find somebody who was actually willing to take the risk to make such a construction, because apparently it's not a very common system what we're trying to do there. So, last 2 slides. What can SYSLAB be used for? I mean, as I said in the introduction already, the main reason we built it was as a test bed for system control concepts. So that's all kinds of things that you can dream of that are not ready to be tested anywhere else than in the lab: distributed control, decentralized control, aggregation, virtual power plants, whatever you name it. That was the original reason why we built it. Demand response is something that has come up quite a lot in the last years. There's a lot of interest in demand response. Actually, our FlexHouse number 1 is the most used component, because a lot of people look at flexibility from buildings and want to play with that. And an activity that we've also done quite a bit is testing of communication protocols, because we have full flexibility, since we have basically a full-size computer for each resource, so we can basically put custom protocols on or test some standardized protocols, and also work with data models. How can you model flexibility? How can you model functionality of units? So they're, for example, easy to aggregate, other things. The other sort of rail of what we're using SYSLAB for is testing of energy system components as characterization of energy technology. So sometimes, we get a component that people ask us to test. And then, of course, it's best to test it if you can actually connect it to a power system that has some other components on it, so you can test it in a power system context. That went too far. We also started developing some of our own resources. That's mostly in connection with the houses. As I said, we've been looking at interaction between heterogeneous, the components of a heterogeneous power system. So that's kind of interaction between components. And then recently, as I also mentioned, we've been looking into multi-energy systems. So go beyond electricity only, but also look into district heating and possibly gas and other energy carriers that we might be interested in the future. I think that was the overview that I have. So the next one is